So we've just opened the DXF file of the laser cut panels. So what you can see here is this is the details come through from the artwork. Now this can come through in many different formats. So we've had it in the past that the artist has provided sketches, and we've taken those as PDFs and then converted them to DXF, which is an AutoCAD type format. And the benefit of that is it creates this in obviously digital lines. We do find that if you can get the artist or whoever's developing the pattern to work in a digital format, it does take out a lot of time. So this particular one was developed by the artist in SketchUp, which is great because it comes through digitally. We converted the SketchUp directly into a DXF file. And here we're just this is Autodesk DWG TrueView. Just allows us to quickly look at the file to make sure everything's good, and we've done some measurements and whatnot. This is a compliant balustrade infill system. So that's what we're looking at here. These are laser cut panels that will go into a balustrade system. So this all looks good. So now we'll switch over into SAP2000, which is our analysis software. So here we are in SAP2000, and we're just going to import our DXF file. So we go into the file, import, and there's a AutoCAD DXF file import function. So we're going to go down to that one. And here's our file we've just created in DXF format. Now here, that file was created in millimeters. So we just want to make sure we import correctly, and you'll see we'll double check that afterwards. And if you select the wrong option, what you'll find is when you start looking at the model, it'll be, rather than 1 meter long, it'll be 1,000 meters. It's pretty obvious to see where you've got your dimensions wrong. The rest of those options are standard. And obviously the Z direction is upwards here. That's what our model was set to. If your model is set otherwise, then just bear that in mind. It might take a little bit of couple efforts to make sure you get the right one, but this works for our modeling. Now what we've done here is our plates, we've just brung them in as line work. Now what we found in the past, if we try and import the actual shell, so the infill itself, it just doesn't work. SAP doesn't really like it. So we've only been bringing in the line work, which is pretty much what your artist is producing. So we bring that in, click OK. Now this should open what looks like our laser cut panel system. Okay, so this is looking from above. We're now going to convert it to the XZ, and you can see, here we go. We have our balustrade system. I'm going to do a few tidy ups. So here we are back in SAP2000. Now, what have we done here? We've basically taken our existing laser cut panels and stretched a solid plate over the top. Now, one of the tidy up elements we did was defining our materials. So we've got a material in here which is stainless steel 316. So that's all the normal property materials for stainless steel. And we've also created a area section which is 6mm stainless steel, which is what we're going to be using for these balustrade panels. So we've got a thin shell element, 6mm thick, using the stainless steel 316 material. Okay, now we've got at the moment showing filled materials, just so you can see that the solid pink is what the panel currently does. It's not laser cut. And what we've got sat in behind there, if I take fill objects off, is the line work, which is the artwork. Okay, so now what our proprietary API is going to do is automatically go through and find these patterns and cut the panel out according to these panels. And then we'll go back in and delete those frames. So those blue elements are frame elements at the moment. They're not cutouts. So we're going to get the thing to cut it out. So as you can see, this matches the DXF and therefore the artwork. Now we're going to make that big pink panel match what we're trying to do. So here we are in SAP2000 again. Now, one of the things I want to point out here is if we zoom in, you'll see we've created a 5x5 automatic grid. Now, this is a very easy one because it's a square. So it is literally 5x5. The reason we've done that is the API system we've run cuts it out on a kind of pixelated basis. So it creates the shape based on removing pixels that are within the line work. So you can see that you want to make sure that you've got enough pixels within the remaining bits to create the shape. And that'll come through in the output. Now we did that within the area editor. So if you select an area, we'll just select a random area there. Within the area section, we were using this divide area using general tool, and we had it set to 5 mil maximum size of subdivisions. And that's given us this 5 mil by 5 mil pixelated mesh that our cutout will now work with. So I'll close that down and we'll go into the SAP API. So what do you do if you don't want to spend your time deleting each of those little pixels? That's when APIs, so automated programming interfaces, come into play. So we've done it within a software called PyCharm. Doesn't matter what software you use. The point of this PyCharm is it allows our computer system to run Python code. Python is just one of many coding languages that can automate the process. Specifically here, we're using Python to interface with the SAP2000 API. They're compatible languages. Within the Python code, we're telling it to open the file we've already created and manipulate certain parts of it. In this particular one, we tell it to count the number of frames, count the number of shell elements, and then systematically work through any of the shell elements that occur within the cutout and delete them. So rather than doing it one by one manually, we can just leave this to run in the background and it will automatically cut out the entire laser cut panel for us. So let's run it on the model we've just created. So the first thing it's going to do is try and open our model. Then it's going to count the frames and the shells. And the reason we do that is just to check it's opened the model successfully and give it a little challenge. Then it runs the long process of doing all the cutouts. And that can run on very, very complex ones. We've had it running overnight. On simple, large cutouts, we're talking a few minutes. It really does depend on the complexity of the model and the complexity of the cutout. So you can see here it's opening up SAP. So we'll come back to this when the process is finished and show you what it's done. So we've just come back and the script has run. You'll see down here in terms of percentage complete. Now it's very incremental because there's just so many shells and so many frames to work through, but it has finished. So if we come out of here and now go into our SAP model, this is the model it opened and did. Now what we've got in the background here is the frames that it used to create that kind of intricate, complex cutout mesh is still there. And you can see the match is pretty strong. Now this is a slightly different approach because like I say, it is a pixelated approach. If we zoom into a detail, you'll see that it kind of, like the old days of kind of computer graphics, everything's made of little squares. So when you're dealing with curves and angles, that can be quite jarring when zoomed in. From a distance, it makes hardly any difference. But it's the speed and efficiency of this process that's the real kind of the wow factor. So the first thing we'll do here is check that model, and it looks like a really good run on this. So I'll do some tidy ups and we'll come back to it. So here we are in the cleaned up model. Now what you can see is we've taken off the frame elements. They've been removed from the model. We've added restraints. So we've got pins along here that represent where the fixings will go. So we've got M10 fixings down this face. And we've put restraints down here, but I've put a roller restraint in the longitudinal direction because we've got slotted holes. And you'll see here, I've got 3 small point loads. All the loading done within the model we've done as nominal loads. So we've done 1 kilonewton point loads, and we've also done surface area loads at 1 kPa. Now the reason we can do that within SAP is then when we come into our actual, so that's in the load patterns, when we come into our load cases, so let's take for instance the SLS wind. The SLS wind has been estimated at 1.4 kPa. So when we come into the loading, we've applied 1.4 times our nominal 1 kPa load. We've run these as non-linear with p delta effects, just in case there's any kind of extra demands that come from the deflection of these systems. And you'll see there's a summary of the load cases. So we've got an SLS wind area load, ULS wind area load. Then we've got a point load barrier. So for barrier infills, they allow for a point load, which just kind of allows for the fact that pedestrians may push on certain elements of the balustrade. And it's a good check for something like this, because if you've got too fine a detail, you might find that it permits someone to bend out of shape your laser cut details, and that's not something you want. So it's good to have a point load check in there. And then we've got the standard barrier infill check. We've got a 0.75 kPa because we're using the visitor structures loading, which is slightly less than normal commercial and residential loading. This is for a remote structure. So we come out of there. So you can see here, that's our point loads. Now, if we go into just go into pure elevation, we'll start looking at some of the contour information. So some of the key things we're looking at here is we want to look at deflections and stresses. So I'll just zoom in down here. So you can see overall that's looking very, very consistent with our artwork. So we'll just give a look at the deflections. Now we'll look at the deflections for our SLS barrier case. Now there is a part of the code, there's no real deflection checks for barriers, but there is part of the code that kind of recommends limiting rail deflection to 30 mil. So we'll use that here for our infill check. We don't want any infill kind of movements over 30 mil, and ideally a lot less. So we're looking at our barrier infill load. We're going to do contours in the Y direction so we can see what's happening. I'll just run that now. And this will give us contour information of deflections. Now we'd expect most deflection to occur through the midspan. Bearing in mind this thing is spanning side to side. So at this scale it's difficult to see those contours. So I'll zoom into a midspan region. So through this midspan region you can see we're getting deflections in the order of 17 mil. Now 17 mil for a 1500 long balustrade panel, that seems in the order of magnitude we're expecting. That's a span over 100 kind of deflection, but that is for a 0.75 kPa load being applied everywhere. You can see over here on the contours are automatically registering that the biggest deflection we're getting is in that order of 17 mil, which is what we're seeing here. So if you look through this middle region, it's 17.3. And then it gradually gets less. I think that is the largest, but that all seems within the kind of order of magnitude. Now we did originally have these balustrades running at 6 mil plate. We've upsized that to 8 mil plate. At 6 mil we were getting deflections close to, but in excess of 30 mil, which didn't feel right. It felt too flexible as a system. And I think that comes from the fact we've got quite a large amount of cutout regions here. So through this mid region, there's not actually a lot of section. So an 8 mil plate seems worthwhile. So the next thing we'll look at is our stresses. So I'll just move that up there. So when we look at our stresses, we can see by inspection there's going to be two load cases that will govern. One will be the ULS wind case, which is just by inspection bigger than the ULS barrier case. So the barrier case is 1.5 times 0.75 kPa, but the wind case is a 2.1 kPa ULS wind. That's our 100-year wind of it. That's our 1 in 100 year. That's our 100-year design life wind, but I think it's like a 1 in 1,000-year event. So it's a pretty extreme wind, and it's clocking up around 58 meters per second, which is a very strong wind. Now we've set it up here to show us shell stresses. We're looking at the absolute maximums. We just want a very quick view on what is the maximum stress, rather than worrying about visible face, back face, top face, and whatnot. And again, rather than the direction of that, we can ask for S-max. Now, what I've done here is I've limited the contour range to 205 MPa. The reason I've done that is so we can use, that's the yield limit on 316 stainless steel. At the moment, we're working with the contractor to consider whether we're using stainless or mild steel. Now, at mild steel, we'd be able to clock up to about 350 MPa. So this is quite a good check. Now, I suspect it will be the deflection that's governed anyway, but we'll look now at the 205. So I'll close that. Now, again, at that scale, you can't really see an awful lot. I'll see if I can zoom in from a distance to see. Yeah, that's pretty good. So we can get a quick view on the world. So around this mid-span region, we're expecting the high ones. We're getting good demands there, generally in the order of about 150. Obviously, there's some high spots around corners, generally not clocking in much more than 200, which is good to see. You can see we've got some blue areas around here, so we'll have a look at that in detail and up here. There's a spot there. I mean, that's 434. I'll come to that later. So let's zoom into this region here. So this is a mid-span region where we'd expect bending stresses to be reasonably high. So you can see here, this shows us the blue, the hot spots where we're likely to exceed 205 MPa. Now they are very localized. They're of a region of 10 mil in diameter, very, very localized. Now, worth noting, this is a ULS case, and we're looking at yield here. So it's a little bit conservative. So one of the things we can do is, these look very close to the yield limits. So there's nothing there that's raising any massive alarm bells. What we can also do is do a cross check to see, right, at SLS wind, hang on, sorry, that's the font shape. At SLS wind, how does this look? So that's a ULS wind case with a little bit of yielding. Now, SLS, we don't get any yielding. There's no blue spots whatsoever. So you can see this thing for its SLS event, which is it's a 100-year design life. So it's a very large wind still, doesn't yield. So that gives us great confidence that this system is pretty robust for what we're trying to do and would work in stainless steel. So there was a hotspot down here. So let's have a look at this one down here. This one's still showing up as blue even in the SLS event. So you can see through here, let me just zoom in even more so it starts giving me the stresses. We've got a high spot. Yeah, it's not giving me the value, which, here we go. So that's 260. Now, worth noting that these, what we call pixels, are 5 mil pixels. Now, the actual detailing put forward by the artist has a minimum 10 mil throat. So this pixelation is just a kind of a symptom of our methods. So what we can see there is actually this bottleneck in reality is twice the thickness of this. What do I mean by that? Well, if we come down here, this is the SketchUp model. That's modeling this region here. Now in that model, it's 5 mil because it's 1 pixel. But if we do a measure, that's 10 mil. So it's twice as big. And you can also see the way it comes into that section is that 10 mil is an absolute pinch point. So I think we can actually confirm, there'll be a lot more ways for that stress to find its way out. So at 260, 280, it could well be half of that in reality because we've got twice the section size there. And if we look at that in the ULS case, I think we were seeing 400 or something. But again, if we were to divide that by 2, because we've actually got twice that width, we'll find we'll be within yield. So let's just see what's happened there. Is that done yet? Just need to apply. Here we go. So this was a maximum we identified from afar. So you can see here, this is 408, 409. Now the problem is that's because that pinch point is only 5 mil. The reality is in the actual detailing, it's 10 mil. So, it wouldn't be unreasonable to say, well, that 400 is closer to 200 because we've got twice the width to carry the same force. So the stress will be half. So overall, I think we're pretty happy that the methods we've used and the detailing seems suitable for an 8mm stainless steel. And obviously a lot of these high points, that would go away if we were to use a mild steel at 350 MPa. I mean, none of these things would be an issue at all. And this one up here you can see is at 200. So it's very much on the limit of the yield anyway, and nothing yielded within the SLS case. So overall, that's a really good outcome. So you can see here, that's the full method on how to use the SAP API to do quick and efficient laser cut detailing to get the right materials, the right thicknesses, and the right connections. You know, we might, if this wasn't going to work, we could have looked at adding stiffeners to the top edges so that load spans in the vertical direction. You can see the way this has been cut out, members are spanning more in a vertical direction than they are across the section. So having a stiffener along the top and bottom, like an angle on the back, that would have done a good outcome. But I don't think that's needed here, and that's an extra complexity we don't really want. And with the deflections in the order of magnitude we were hoping for, I think we're good to go. So thank you for watching this, and I hope you've enjoyed it and learned something. And yeah, get in touch if you want to find out more about the SAP API and laser cut detailing.